Okay, so I'm back with the second part of the lecture for Module 3, and well, at least week 4, Module 3, week 4. And I left off with histogram. Histogram to me is one of the most important graphs that we can that we can have when we're looking at our data. And I want to show you what it looks like because it can show you how our data is distributed. And so when we're making assumptions about statistics and whether we meet assumptions, a lot of times statistics are built around a number of assumptions that if they violate them, it could render the statistics, the whole study, the whole instrument invalid, which means it's not accurate, right? And so, a lot of us going into this, may not have a big idea of why stats, why we do the things that we do. But one of the things that we really look at is we built a lot of our science on this assumption that things are distributed in a bell curve, a Gaussian curve, a normal curve, normal bell. And so a histogram allows us to take a look to see where most of our scores are distributed. And so I will share this now. Let me go ahead and draw it for you because you should know this ad nauseum. If you're going to take a comprehensive exam, if you're going to, do anything with stats, there's this basic assumption that we're building our ideas around the assumption of a bell curve, that if we have 100 people and we all take an IQ test, most people are going to be around the mean, be clustered around the mean, and you're going to have a few people that are really low in IQ or really high in IQ. And, to have a valid psychological construct, the same thing as if we all 100 people lined up in a race, you'd expect a bunch of people to be clustered around the middle, around the average, around the mean. A few people, a couple of people would be really fast, maybe a couple of people, 4 people would be really slow. And so I want you to get an idea of, what we're assuming here. And so this is a whiteboard, and I'm going to draw on it, hopefully, if it will allow me to. And let's see here. Here's a pen. So let's say that we have, I'll take IQ, for instance. And IQ, it's assumed that the average IQ is 100. That's the way these IQ tests have been built. And you have clusters of scores within 15 IQ points. And so the standard deviation, we'll get into what that is in subsequent chapters, but the standard deviation on most measures of IQ is 15. And so you start to cluster people a lot around these particular anchors. Actually, if you're going to qualify for disability, your IQ has to be 70 or below. So you can see it's 2 standard deviations, 1, 2 below. And in this case, the mean is 100. It also represent mean by X, 100. So you might see these interchangeable, depending upon whether it's a population or sample. Okay, but what we assume is that most of the data, most scores, most people out of let's say we have N equals 100 here, 100 people. Again, small n would be a sample, big N would be a population. Let's say it's just a population number because I don't want to go back and make my small n. So what we assume then with this data is that 30, and if I'm drawing lines here, let's say 38% of people lie within 1 standard deviation above the mean. 38% of people would fall in 1 standard deviation below the mean. You'd have another 14% of people that would lie between 1 and negative 1 and negative 2 standard deviations below the mean. You'd have 14% of people that would lie 1 standard deviation to 2 standard deviations above the mean. And then out here in the tails, you've got approximately 2% that are looking at Mensa, and you've got approximately 2% that are possibly looking at a disability. So that's the way that we assume that most data is clustered. And most statistics are built on this assumption of a Gaussian, a normal, a bell curve. And so if you put +1 or -1, 68% of people are here either +1 or -1 away from the mean. Another 28% out here are, one standard deviation, at least 1 to 2 standard deviations above or below. And then out here in the tails is about 4%. I would, you can tell I just reeled that off from memory. It's important. I would say if you're testing, you want to be able to produce these and maybe not an IQ. I mean, so we could take another construct. We could take depression. We could take happiness scores. We could we could all race. It's the assumption that most phenomenon occur within a normal distribution here. So let me stop my share. And now let's go look at a histogram that's in our textbook, because that's really what a histogram is based around. This idea that you can get a visual on what your data, you can get a visual on what on how it looks. And that's why I would argue that's why a lot of this is very important when we come to these charts, these histograms. So looking at this is from our textbook. This is from page 91. You'll see that your textbook has a histogram laid out here for moral relativism scores. And so first off, do you notice it looks pretty similar to a bell curve, right? And you're like, well, what about these two tall, these things here? I wouldn't get too wrapped up in those. Again, it's trying to it's not an exact representation, but you want your data to look very similar to this. If you're to build your own instrument, if you were to build an instrument that's measuring anxiety, that's measuring narcissism, you want your instrument to look very similar to this, and that a lot of people are going to be clustered around the middle, and then you're going to have a few people that score really very high or really very low. And so this is a way that we check for if what we're doing, it meets assumptions. This is the assumption of normality. You can see a scatter plot below. We're not going to talk about scatter plots right now. But again, you can see that out of all the people that took this moral relativism scale, most people are scoring here in the middle. What was neat about my dissertation is when I ran my data, I had a very normal curve. There are a couple other things that we look at when we're looking at the histogram. We could have a negative skew, which means that you have people that are scoring higher on the scale, which a negative skew just means that the distribution slopes back to the left. A positive skew would be the exact opposite. You'd have a lot of scores on the lower end, and it would slope to the right toward the positive end of things. So I'm going to stop there because I know, I can start to get really excited about stats. It's usually good to break up my voice. I'm going to share a couple of videos about the stem and leaf, and also the box and whiskers. Box and whiskers sounds fun. Sounds like you need to, get it a litter box and feed it some kibble. So again, this really ridiculous stat humor, but I hope that you found this beneficial. The other thing that we talked about, it's really simple. As far as one of the last concepts I want us to get, and this goes to stem and leaf and box and whiskers, is the range. So both of those visualizations will give you the range, I think, a little bit better than a histogram does. So what the range of a distribution is, if you'll go down here with me into our discussion. The range is simply taking the highest and the lowest score and then subtracting them. So if you had scores that range from 60 to 95, you take 95 minus 60 and your range is 35 points. It's pretty easy to calculate. Now, we're also going to get into variance and standard deviation. And so I'm going to stop the video because I do want to talk to you a little bit about that, because this is where, figuring the mean and standard deviation is very important because it allows us to then get a look at, like my drawing was, it gets us to look at a very detailed picture of what our distribution of scores looks like.